Alrighty, let's get started today. So last time we went through some derivations of the Lorentz transformation for special relativity. We found that the transformations go like this. X prime, which is the x coordinate, the position or the length or whatever, the distance, in the reference frame of a moving observer, is equal to gamma, which I'll talk about what gamma is in a little bit, times x minus ut, where gamma is 1 over the square root of 1 minus u squared over c squared. X primed stuff, s prime, that is the coordinate system that's primed, is for the object or for the observer which is in motion relative to the other observer. So again, this is relativity, which means no one observer is the non-moving observer. Both would say the other observer is moving relative to them. But what I mean is, once you assume one of the observers to be stationary, then the other observer is the one in motion, and they would get the prime coordinate stuff. You, assuming you're the stationary one, all of your x and y and t coordinates would be for the non-moving coordinate system, the non-moving reference frame, and so you would have the unprimed coordinates. Okay. U is the relative velocity between the observers. So if you think about something like you're standing on Earth, you're looking out into a sky, and a satellite moves past the Earth with a certain speed. Well, you obviously would assume you're the stationary person, so you would get unprimed coordinates, and the satellite would get the primed coordinates. So if questions were to be asked about times, how long does it take for such and such to happen relative to, or according to you, you're looking for t. Whereas if you want to know how long would the satellite say it took, then you're looking for t prime. And u is the velocity of the satellite relative to you. Of course, if you're a little person on this satellite dish, you would say, no, actually it's the Earth that happens to be moving past me. So that person standing on the Earth looking up at me, they're moving. So when I calculate time, I would calculate t, and they would be calculating the t prime stuff. Okay? And neither of us knows which one's right, and in fact, relativity says neither of us is right, and both of us are right. There's no way to experimentally verify actually, technically, the Earth is stationary relative to the background of the universe or something like that. There's no such thing. So you always state one of the observers is the stationary one, and then the other observer must be the one in motion, and they would get the prime stuff. Okay? So there's our x transformation, our t transformation, t prime is gamma times t minus ux over c squared. And then the easy ones, y prime is just y, and z prime is just z, because the only interesting effects are in the direction of motion. And since it's always true that you can rotate your coordinate system in such a way as to make all the motion along one axis, and thus all the boosting you do, all the transformations you do, you only have to worry about it along one axis, and it's just standard procedure to make that the x-axis. Of course, you could go the other way around. You could say, well, if this is what I on the Earth would say the person on the satellite is going to calculate or measure, what about the other way around? Well, to go the other way, all you have to do is replace all your velocities u in these equations with the negative version of it. So x is gamma times x prime plus ut prime. T is gamma times t prime plus ux prime over c squared. And then these don't change, obviously. And z. Okay, so there we go. There are the two transformations, depending on which coordinate system it is you're trying to calculate. Now, what we want to do today is a couple of examples of what calculations we can do using these transformations. And along with that, what are some of the implications of this being the way relativity works, this being the way you transform, rather than the old Galilean transformations. So let's take an example. So let us say a spaceship travels at 0.99 times the speed of light past the Earth. The pilot claims they have been flying for 3 years. How long would an earthly observer say they have been flying? Technically, for how long, but there you go. For how long would someone on Earth, an observer on Earth, say this spaceship's been flying? Okay. Now, the most important thing whenever you're doing relativity calculations is to understand, number one, what is it asking me to find? That is, am I trying to find a time, a speed, a length, a distance? And once you know that, of course, in this case, we're being told for how long was this rocket moving? We're looking for a time. Okay, so I know I want either t or t prime. Now the question is, which of those am I trying to calculate? Am I looking for t prime? That is, am I looking for the time according to the moving observer, or am I looking for t? Well, of course, here, we're told what t prime is. So this right here, this 3 years of travel, that's t prime. That is, according to the observer which is moving. You're the observer that's not moving. You're the person on Earth. You're looking out at this rocket or spaceship. It's moving past you. So you say the spaceship is moving. So everything the spaceship says, that's primed stuff. So they claim they've been flying for 3 years. Thus, t prime is 3 years. You're looking for t. You're looking for what you say the time actually is. And you're not moving. So you're unprimed. So what we want is to find t, given we know t prime, and of course that's gamma times t prime plus u x prime over c squared. All right, good. Now, what do we want to do? Plug numbers in here. Gamma, that's 1 over the square root of 1 minus u, well, that's just 0.99 times c, over c, and all of that is squared. Right? That's our gamma, u over c squared. That's multiplying time. Now, remember, we're physicists here, so units are going to matter to us. Notice that in gamma, I've already assumed, or I've already forced the units of velocity, u, to be in terms of the speed of light. So so many times, 3 times 10 to the 8th meters per second and whatever. Or, 1 light year per year or whatever it happens to be. But here in this binomial, t prime plus ux prime over c squared, remember you can only add 2 numbers together if they have the same units. So whatever units I use for the time t prime, then the second term better also come out to have units of years, or whatever units I use. Now, one thing you can do is just put everything in terms of meters per second and all of that stuff, our normal metric system. Or the other thing we can do is make use of the fact that certain terms are going to drop out here and just use the units of time given in the problem, which is years. That way we don't have a bunch of decimals and stuff like that. So you'll see what I mean in a little bit. For now, I'll just call it 3 years instead of converting it to seconds. And thus, the answer I'm going to get is going to be in years rather than seconds. However, that's only going to be possible if either this next term is 0 or the next term has units of years as well. Okay? Well, let's look at the next term. The next term says, look, you've got u, x prime, c squared. U is how fast the ship travels. C squared is c squared. X prime is the location of the ship according to the person on the ship. So when you're looking at the ship fly by and you say, okay, now that's where the ship is located, you would say that position is X. Well, to the person on the ship, their own coordinate system has them at the origin. Why would you not put yourself at the origin of your coordinate system? And since they're at the origin of their own coordinate system, they would say their ship is located at x prime equals 0. So this term is just 0. And now we're okay with our units because it's just 3 years, so the answer I get for t is going to be in years. If, however, this second term did not drop out, then all we'd have to do is make sure that when we plug in our u, our x, and our c, that the final units they would give after you multiply everything out is also years. So meters per second is not going to work. I need some kind of light years per years or some weird unit system. Or, like I said, the other thing to do is just convert everything to meters per second and kilograms and things like this, and then the final answer would just be in seconds. Okay? All right, so there we go. There's all our stuff there. Notice the c here cancels the c there. That's why in relativity, we're almost always giving velocities relative to the speed of light, or as multiples of the speed of light, so that the c's go away. And now I just want to plug everything into my calculator here. What do I get? So 0.99 squared, 1 minus that answer, square root of that, 1 over this number, times our 3 years. And what I get here is that to you, the observer on Earth, watching this spaceship fly by, you would say the spaceship's been flying for 21.3 years. Very, very interesting. So you say, look, I've been watching your spaceship this whole time. I've had 21 birthdays. My milk has gone bad in my refrigerator. Whatever you want to say, it's been 21 years. But the pilot of the spaceship, they say, no, it hasn't. I've got my own watches. I've been tracking the time. I've only had 3 birthdays since we took off. And everybody else agrees. No one's tricking me here. No one's playing some kind of weird game. It really has only been 3 years. And the worst part is that to the universe, you're both right. Neither of you can say the other person's actually wrong. It is true that for you on the Earth watching this spaceship fly by, it's been 21 real years. It's also true that to the pilot of the spaceship, as they're flying by, it's only been 3 years. And this is what makes relativity so interesting, and why at first it was not really believed that this is actually how the universe works. How could it possibly be that 2 observers seeing the same event, which is this rocket passes by the Earth, would disagree on how long it takes for this event to happen. But not just that they would disagree, that's perfectly reasonable. Of course that's going to happen. The part that's unreasonable, but still true, is the fact that they're both right in what they say. It's not that the guy on the spaceship is wrong, or the person observing this saw something strange and just miscalculated or whatever. No, they're both completely right. Both answers are true. The rocket's been out there for only 3 years, but it's also been out there for 21 years. And any amount of time you want to talk about, according to a relatively moving observer. Okay? But this is how you go about doing this kind of time dilation stuff. An object moving with some velocity relative to you, you count as the unmoving person. The rocket's the moving thing. So for your time, t, you're calculating how much it is compared to what the rocket says their time, t prime, happens to be. Okay? Let's try another example. All right, for this example, I want to do length contraction instead of time dilation. The last one was time dilation. Now we're going to talk about length contraction. And in order for this to work more easily, I'm going to give you the straight up length contraction equation that you can use anytime you have a problem like this. And it goes like this. These are the standard variable names. Basically L is equal to L naught over gamma. Okay? Where L naught is the length according to its rest frame. Sometimes that's also called the proper length. And L is the length according to an observer in relative motion. Okay. So let's see what happens. Here's an example. We have a 1 kilometer long rocket. Now this is how long, obviously, we're talking about length contraction, so giving a length of something, we always have to talk about relative to what or according to whom. And so we're saying, let's say you're up in the star yards creating these spaceships, and while it's in dock, you measure the length of this rocket and you find out it's 1 kilometer long. Okay, so according or while, let's say while stationary. Okay, so that's how long this rocket ship is. This rocket flies by the Earth with a speed of 85% the speed of light. Okay? The question is, how long would an earthly observer say the rocket is? Okay. So here's the picture. Here's the Earth. There you are as the observer. And here is a little rocket ship flying past you with a speed v, or u, is 0.85 c. And the question is, if you were to measure the length of this rocket, what do you say the rocket measures? Okay, we know that to someone on the rocket, that is, the rocket's not moving relative to them because they're on the rocket. If they get their tape measure out and measure this thing, it's 1,000 meters. But you're seeing this thing fly by, so what do you see? And that's where this length contraction equation comes from, or is for. We would say, well, the length you measure is 1 over gamma, and remember, 1 over gamma is the same as the square root of 1 minus u over c squared times the actual length, or the proper length of this rocket ship. So the square root is 1 minus 0.85 c over c, quantity squared, times 1,000 meters. And what do we get? Well, again, the c's cancel here, so I get 0.85 squared, 1 minus that number, square root of that thing, times 1,000 meters, and I get that, according to the person on Earth watching this rocket fly by, they would say the rocket measures a length of 526.8 meters. Less than the true length of the rocket according to someone who built it, or according to the specifications, the blueprints. Someone out there, some engineer, built this rocket, found it to be 1,000 meters long. They sent it out into space, and as it's traveling by, you look up and measure it, and you say, wait a second, it's only 526 meters long. And yes, that's true. However, if you call the pilot, you say, hey, something's wrong with your rocket, half of it's missing. They say, no, it's not. I just measured the length of my rocket. It's still 1 kilometer long. What are you talking about? And again, we come to this point in nature where they're both right. Neither is wrong, neither is miscalculating, neither is measuring. They're both using proper tools, and they're measuring the correct way, and they just disagree on what the answers are. And actually, it's these two combinations of things, the length contraction with time dilation, that allows for the fact that the speed of light is always constant, or always measured to be the same, no matter how the observer moves. And of course, no matter how the source moves. By measuring the speed of light, you have to find out how far did it travel, how long did it take, and both sets of contractions and dilations and things conspire to give C is always C no matter what happens. The gammas tend to cancel out. But that's the important thing here. If you have a moving object, their time is always slow. Okay? If you have a moving object, their length is always shorter. Every time. And that's because gamma on the top or the bottom, well, if gamma's on the top, then it's always going to reduce. If gamma's on the, if it's on the bottom, it's always going to reduce. Because 1 minus V over C, 1 minus U over C, that's always a number less than 1. Square root of that, still less than 1. So if you multiply by a number less than 1, you reduce. You get length contraction. But when it's on the top, the square root is now on the bottom. So you have a number less than 1 on the bottom. It's going to blow up your number. And so you get time dilation. Times grow. Because, one way of thinking about it philosophically, is because your clock ticks slower, when I look at your time, I would say it's a lot longer than you would say. Okay? Because according to you, your clock ticks fine, but I say no, it's ticking slow, so when you reach 10 seconds on your clock, it's actually really been 30 seconds. Okay? So time dilation. Time gets longer, distances get shorter, in such a way as to always keep the speed of light constant. Now, any relativity problem, at least the simplistic special relativity problems, can be done in this fashion. You're looking about how the times compare. You use our normal Lorentz transformation stuff. If you're talking about length contraction, this is just a quick little easy thing. Of course, if you want to derive this, you just start with the Lorentz transformations, and you do x2 minus x1 and x2 prime minus x1 prime, keeping the velocities constant for both, plugging things into each other. Eventually you get down to this particular equation. I wanted to skip all of the derivation because at the end of the day you could follow the derivation if you want, but this is the useful bit. This is what you will use to calculate. So with that, I hope this is helpful. Next time we will look into the vectorization, I will call it, the more formalizing the mathematics for relativity, noticing that the way these Lorentz transformations seem to kind of mix space and time coordinates. You notice here, x has t's in it, and the equation for t has x's in it. That's very, very similar to vectors. This is x and this is y, and I have some vector sitting out here in space. Well, this vector has a particular x component and y component. But then if I get a different coordinate system, so maybe my coordinate system looks like this, where this is my new x prime and this is my new y prime, then I could figure out how to transform from x to x prime and y to y prime. And of course, you could either use transformation matrices or rotation matrices. But basically, you get cosines and sines that say the value of x prime is kind of a combination of x's and y's, and the value of y prime is a combination of x's and y's, but just mixed up with each other. The same seems to hold for x's and t's here. So there's some sort of mixing, some sort of like a rotation, but instead of it being just in space, rotating x into y and vice versa, there seems to be a rotation from time and space. And while it's not exactly a rotation, and I'm warning you now, it's not just cosines and sines, it's a slightly more complex version, but the analogy will hold. Vectors are defined in mathematics by the way they transform. We will find that we could create a vector-like thing, that is to say, something that transforms like a vector, thus it's a vector, but instead of having x, y, and z as our components, we're going to have 4 components time x, y, and z. And then, of course, once we have this, now we can do all of our old vector mechanics, all of our old physics problems and everything using a new coordinate system, a new set of vectors with 4 components instead of 3, following the rules of relativity, following the rules of how you transform from one vector to another, and we'll be able to rederive all of physics relativistically. And hopefully, in having this new reformulation, can we get back to our old Newtonian physics that seems to work under those assumptions where the velocity is slow and things like this? So that's what we'll do next time. Look at how we can formalize relativity and formalize these coordinates into a 4-dimensional vector. Because once we can do that, we already have all the mathematics of vectors, so we just apply that mathematical structure to a 4-dimensional vector instead of a 3. Okay? So, until then, I will see you next time.